Computing over the last 70 years has been based on Boolean algebra, where operations are performed on binary code using just two digits, 0 and 1. These ones and zeros are represented by the on and off states of transistor switches, and the binary code developed through combinations of these two digits can represent numbers, letters, or a position on a computer screen. Today's microprocessors contain billions of transistors, allowing the dizzying array of computational capabilities which are packed into modern-day mobile phones and laptops, all the way through to supercomputers. Our current transistors and memory elements, which represent binary bits, are based on controlling electrons in semiconductors. But these devices do not rely upon or try to exploit the peculiar quantum behavior of individual electrons or pairs of electrons. In the quantum realm, electrons can be in a superposition of multiple states and also exhibit the property of entanglement, where an operation on one electron can affect the property of an entangled electron instantaneously across space. These properties of superposition and entanglement open the door to a new computing paradigm based on quantum bits, or qubits for short, where the qubits could be based on electrons, photons, or the nucleus of an atom. Operations on two entangled qubits can perform 2 to the power of 2 calculations, 3 entangled qubits 2 to the power of 3 calculations, and so on, with n qubits capable of 2 to the power of n calculations, allowing computations which would not be possible within practical timescales using current binary code-based computers. To move into this new realm, exploiting quantum effects, it is necessary to operate quantum circuits at extremely low temperatures, typically below 1 Kelvin, where the superposition and entanglement properties of qubits can be maintained for sufficient periods of time to allow computations to be performed. This is what a current experimental quantum computer could look like. The qubits are in the refrigerator, where the temperature is less than temperatures in deep space, and all the electronics needed to read and write at high frequencies to the delicate qubits are outside the fridge at room temperature, around 300 degrees C hotter. This approach can be realized for a small number of qubits, but this raises the question, how many qubits are needed to make a practical system? Accounting for the need to run error corrections, this could be up to 100,000 qubits and beyond. With this number of qubits, there won't be a way to get all the cables into the fridge. It is clear there are fascinating engineering, as well as scientific challenges, on the road to a practical quantum computer. This is where the Sequence Consortium is focusing its efforts, by exploring routes to integrate the read, write, and control electronics with the qubit circuits at ultra-low temperatures, allowing systems to be scaled up to qubit numbers which are needed for practical quantum computation. And this has an added benefit, as semiconductor-based electronics works better at low temperatures where there is less thermal energy to scatter the motion of electrons. This allows design co-optimization as well as making a more compact and practical quantum computer. The Sequence Consortium has European partners spanning materials and devices, cryogenic modeling, control circuits and 3D integration, all the way through to applications. And the technology being developed has other cool applications beyond quantum computation, such as satellite communications, next-generation radar, and high-performance computing. The project is supported by the European Commission, and the Sequence Consortium are working together to move Europe further forward in one of the coolest hot topics of our age.